Welcome everybody to the October DPRG monthly meeting, and our speaker this month is Scott Gibson. And Scott is the builder of the world famous CanMan, who skunks everybody at all our competitions. Maybe not this time. And anyway, he's going to talk to us about lidars. So this is going to be very practical, and this is Scott's how Scott has done it on CanMan. All right. So yeah. Welcome, Scott.
And by no means is this the only application or implementation that's possible. So, thanks, Doug. Like I said, been asked to talk about the rotating lidar, which is basically a single point lidar that continuously spins. And this is a graphic of it. Most people have seen what's on my robot here. So basically, here's the device. It has a motor system to spin it. It actually has like an encoder positioning that's in the bottom of the collar here. This whole cap spins, and it has basically like an encoder that keeps track of how fast it's spinning, and it sequences the pulsing and the samples based on that feedback. And then, of course, these here, there's an emitter. It's a high frequency light emission, and then a receiver that comes back. And you can see that kind of here, and that's how they do the distance measurements. So they send the pulse out, and then the time and the reflection. So basically, LiDAR is just a time of flight, right, with a different wavelength of light that they use. Now, it is susceptible to UV, so because it's not that high of a frequency. So outdoors, it could be problematic, or like when we used to have contests down at Fair Park that had the huge windows, and the sunshine would come in and basically blind everybody's robots. And then the additional piece of data that you get is your data, or where in the rotation that sample came at. And basically what happens here is you get, as the thing's spinning, and it's kind of hard to see on this screen, you get 360 samples on every rotation. And this thing rotates at, I think it's 4 or 5 hertz, so you get a pretty good throughput. And there's a lot of data to filter through. So like I said, you get 360-degree sample. So a lot of times, and we'll get into some of the software a little bit, is I narrow it down. I ask for a particular range. Like for instance, one of the things I do, or have tried to do, is do obstacle avoidance with it. So at that point, I just look at what's in front of the robot. Because if you're going towards it, it doesn't matter what's behind it. Right? You're not going to run into it if you're going away from it. So a lot of times, you'll see in the software that there's a lot of filtering or ranging that, so we don't have to do all of the samples.
What distances is that one good for?
I'm sorry?
What distances is that one good for?
Actually, I think it's
5
on
meters.
this other screen. Yeah, a distance more than 2,000 times. Basically, I think it was on one of these.
I think it was 5 meters, wasn't it?
No, it's more than that.
Oh, okay.
It's like 10 meters.
Oh, okay.
Yeah. And you'll see that I've got a little, what they call the frame grabber, and I'm going to demonstrate, and you'll see the range that I'm talking about. It's pretty substantial, and it's very, very accurate. It's amazing, because the reading you get back on this one is in millimeters. Mm-hmm. So the range is based in a millimeter count. So you think about how much resolution that is, at 25 millimeters to an inch, right? So a 1/25 of an inch. And also, like you see here, you got 5.5 hertz when sampling 360 points. So that's basically 5 revolutions a second, right? Mm-hmm. So you get, and that's one of the things I've struggled with in the implementation is just dealing with the bulk of data and also the frequency of the data coming in. Because I mean, it just, I have this set up on a UART. I mean, most of the interfaces will go either, you know, SPI. I don't know that any of them run I2C. A lot of them you see, especially like the 3D LiDARs, which do the entire, you know, the range. A lot of that's USB. So I just have this set up on a UART, and in my implementation, it's all just interrupt driven. So I have a 360 element array that I just continuously gets updated by interrupt. And then I can just sample that data anytime I want. And I know that that's going to be the latest scan, right? And at 5 hertz, you know, it's going to be pretty much real-time data, right?
Your robot's not going to move that far
Right.
in 1/5 of a second,
And is it,
unless something's really wrong.
and you mentioned 3D.
Never built a robot faster than you can run. I'm sorry.
Yeah, you mentioned 3 dimensions. Does this kind of scan in 2 dimensions then?
Yes, it basically, and I think that's kind of what you don't see in this slide here, is this is a very level plane, and the dispersion of the pulse is very small. So you only get, it seemed like when I was doing this presentation, it said like a 5 millimeter dot, basically. But the thing you run into is that the further away it goes, of course, the more the beam's going to disperse. So then the less return you're going to have. So your resolution or your accuracy actually starts to fade the further out you go. So it's much more accurate and detailed up close. But again, you know, this is, I'm pretty sure it's 10 meters, so you're talking, you know, 30 odd feet. So you've got quite a bit of range.
Can you
get
miss
out of it.
things like, because I know the beam's dispersing, which is helpful in a way, but does it create like spokes, like will it miss a table leg? You know what I mean, potentially, or you'll have a scintillating return.
Well, no, because as it continuously scans, you're
You'll get
scanning it 5 times a second,
Okay,
right?
okay,
So,
filter that.
and especially if the robot's moving, you may miss one scan,
Right.
but typically, and you know, I mean, I'm speculating here because I've never really tried that.
Right.
And I never really got the obstacle avoidance on this robot working that well because, of course, this is above where the cans are gonna sit, right? So really, the only obstacles that you would have would be the walls, which is really what I key off of in this particular implementation. And that's one reason why this is above where the cans would sit, so that you don't pick up the cans. Basically, I use it here to just augment my odometry and to update it, like especially like in you know, the soccer one where you may bump into somebody else or they may hit you and it's going to throw you out of, you know, off of your odometry, right? So I'm constantly updating the odometry based on it, and that's what we'll cover later when we're looking at the software.
Hey, Scott, you're going to fire up an actual console, right?
Yeah.
So when we do that, why don't we just look at it? Let's because it'll be fixed.
Yeah,
right?
okay, there we go.
So what we
can
can
do
do
the table
is spin around. We can just, at different distances, take an object and try and move it through and see if we find a spot it misses.
Well,
Talking
what,
about
I think
skinny
what you'll
table
see
legs or
is on
flat table legs?
the resolution on the little screen grabber screen that they have isn't all that great. And it's also, the ranging on it is really awkward because, well, you'll see it's like a radar screen, but the outside of it is scaled for the maximum distance. So if you're like right up next to it, then the dot that represents that vector is you know, right up next to the center.
Yeah.
Right, so when you're only like 2 or 3 feet away, that's only 10% of its overall range, right? So, okay, so, and this is just an example of what data, and it's hard to see in this, it isn't, because I had to do a translation from PDF to PowerPoint, so the resolution was lost a little bit, but you can kind of see what the output from this particular scan is. I don't know, does that help?
Doesn't help much, does it?
Okay.
So anyway, you'll see that better when I do the screen grabber thing,
Yeah.
when I start yapping and get into the interesting stuff. Any more questions for me?
So with the Nito lidars, we kind of found that if you're too close to a wall, there, you know, the angle is so shallow that you really don't get a good reflection. So you could be missing, you know, a whole string of data points. And have
Right.
you found that happens with that, or?
I haven't noticed it, it might, but of course, you know, physically, the LiDAR can only get so close to another wall
Right.
on this particular robot. So it does wash out. And one thing that I have found is if you don't have a good solid edge to detect, like for instance, where Doug's at with the tripod there, it's basically just going to get erroneous data there.
Oh.
And I'm fixing to talk about the data packets that you get. And one of the elements in the data packet is the quality of the signal. How I think they call it the confidence level. In other words, how confident are they of this?
Right.
And one of the things I do in the serial routine is I look at that value, and if it's below a certain level, I just ignore it.
Mm-hmm.
And one of the things I used to do is I would put it to basically to 0.
Mm-hmm.
If I didn't know if the confidence level was too low, you have to set it to something, right?
Right.
Either you leave it what the last scan was, or you set it to some arbitrary
0 or
value,
max.
one way or the other. And I set it to 0, and then when I started playing with the object avoidance, it screwed it all up because now it thinks that there's an object 0 distance in front of it.
Mm-hmm.
So then I had to flip around and I put it to the maximum value.
Yeah.
And now actually I think I just leave it, if it's not above the confidence level I want to see, then I just leave it from the last scan.
Mm-hmm.
But you see that a lot, especially on small edges or surfaces that aren't really well defined.
Yeah, that kind of happened, a similar situation with us. We had a display that would, keep up with displaying all the data points, and, of course it has to be scaled because some of the displays
Yeah.
can be pretty small. But, yeah, if you put it to 0, you could have a lot of points at 0 and not know, and so, then it was like, okay, well, stick it out at the max, and at least you get a circle.
Right.
And
Basically, then you're ignoring it. If it's
Yeah.
at the max, then, from an obstacle avoidance issue, you're basically ignoring that scan.
Right.
Right.
Yeah.
But then you start running into things. So that's why I'm pretty sure I left it back to, I just leave it at the last scan. Because I'm getting 5 scans a second anyway. So, another, 200 milliseconds later, I'm going to get a whole nother packet. All right. So I think the next thing we're going to talk about is actual data that you get from it. And my serial routine loads this into a structure. So you have the distance value in millimeters of what that angle is. And then you have the heading, in other words, this is the angle of that measurement, right? Because you got the distance and the angle so that you can correlate it. But what I end up doing is in my array of structures, the heading is the index. That way when I scan through the data, I can scan through the array as an index. And index 0 is position 0, and index 1 is angle, degree 1. So I don't store that data. And here's the quality level, the quality of the measurement. And I think it goes from 0 to 7 or 8 or some weird number. And I don't remember if the low number is good or bad. I didn't include the whole data sheet. I didn't think that was really it. And plus, this is an older model. They make more streamlined, cheaper ones. I mean, this thing was like $300 5 years ago, or however it was when I bought it. Now they sell a better model for like $100, right? So, but I would presume, because the RoboPeak is still making these things, so I presume that the data is fairly similar. It would have to be. And one of the lower cost ones I looked at when I was selecting that one didn't have this quality setting in it. And I think, Ray, the one you were using didn't have it, or didn't you have? Weren't you playing with one at one time?
The Nito, yeah, the Nito ones have that.
Oh, did I?
Yeah.
So you completely refresh that array every interrupt. So like, if
Well, the interrupt is a character interrupt. So I have a state machine that follows this packet. And, you know, basically, because there's a little header or start bit or start flag, so you have to be able to resync on it at any given time or know that you're at that. And actually what I do is I have an array that I build as the data comes in, and then when I see the start flag, which is the signal for a new scan, then I just do a mem copy over to the array that I access.
okay.
That way there's also no contentions of the access, you know, writing to it and
So
accessing.
it's basically it's not a composite image. It's basically every rotation is one array.
Yes.
Yeah.
And that array is updated 5 times a second.
Yeah.
And basically, in that array, I have a distance and a quality reading, and I go ahead and store that, I believe. Well, actually, no, I don't think I do. So really, the only thing I store in the array that I access is the distance, and then that distance, based on the index of the array, is what identifies what angle that distance is at. Because I've already qualified the reading that I've put into the array based on the quality setting, so there's no reason to store that.
Is your start flag FA? That's what it is for the LiDAR, or the?
You know, I don't remember.
Yeah.
I mean, we can look at the code if you want to.
I think
But
these are
it seemed like the serial interface was really convoluted, trying to catch the flag. I don't think it's just a regular, I think it's a repeated start bit like you would see on an E-square
Oh.
bus. But I mean, we can look at the code and I can tell you.
Is that an absolute heading, or is it relative heading?
It's absolute to the device. All right, in other words, here, 0 is the front of the device here. But I have it turned 90 degrees, so I have to do the translation. And I do that, I think I do that when I load my array. So this, to me, is always 0. If that makes sense.
The front of your
From the robot.
front of your platform.
I have to rotate
It's a relative
the
heading
scan data.
based on your IMU, right? So your
Oh, yeah,
IMU
from-
tells you your actual heading, and this is a relative heading.
No, it's just simply rotated 90 degrees clockwise. All of the readings are rotated 90 degrees clockwise, and then that way, because it doesn't matter whether the robot's angled, you know, at 45 degrees, this is still 0 degrees relative to
Yeah.
the position of the robot.
But if this was absolute heading, right, that wall would always be in the same place that in your array, right?
If it was, yeah.
If it was an
fixed.
absolute heading.
With respect to the
So, yeah, even as the robot changed, it would be an absolute heading, but it's not doing that. It's relative to where the robot is pointing.
Well, yeah, and you'll see that in
You
the...
offset that with your IMU, I imagine.
Well, no, you'll see that in the code, because I'll have most of the functions where I determine things,
Yeah.
like whether I'm in the middle or not, in the middle of the course, I pass in what my current heading is. So if I'm, say this table is the CanMan course, right? And these are the 2 sidewalls.
Yeah.
And my robot is at say a 45-degree angle like this. Then when I call the function that measures to see how far from the center of the course I am, I pass it 45 degrees. So it knows to take the LiDAR data and use the angles that are perpendicular to the walls and not within the frame of where the robot's at.
Makes sense.
That's really the only way you can keep, you know, mental sense of it, is because this is always 0 in the LiDAR data. Because depending on how you want to use that data, you can always, like you're saying, kind of offset it or put it in a relative context of what the position of the robot actually is, right? And this kind of gives you some of the specs on it. Like I said, you can actually slow the thing down or speed it up. So you can go down to 1 hertz or 5.5 hertz as far as the scan time. So this just gives you some statistics on what the actual scanner will do.
Yeah.
And you'll see here, I guess it's 6 millimeter or 6
Probably
meters.
6 meters, yeah. Because that's about what the Nito LiDARs are.
Yeah, 6 meters. But that's still, 18, close to 20 feet, right? So,
Radius,
and of course, they make a big thing about, the LiDAR pulse is low enough power that it's not, won't damage a human.
yeah. Draw a line across your right.
Yeah. And here's the graph of the resolution, right? So basically, your resolution is the red line. So and this is your distance here. So as up close, your resolution in millimeters, or your percentage of change is almost 0, up to about 20%. But I found in my practice, which basically is limited to the CanMan course, which is 7x10. That's the maximum distances that I really ever work with. So you're talking about something in this neighborhood. So the accuracy, I know I can tell, and I don't know if you've ever noticed before the contest, I'll go around and I'll square up the
angles?
walls, because our walls have joints in the middle, right?
Mhm.
And I can detect that the walls are angled. And I actually limit it. When I'm measuring the center of the course, I say, well, if it's not within the, 7 feet, 80, 92 or 84 inches, whatever 7 feet is.
Mhm.
If it's not within a couple of inches of that, then I ignore it. Because I'm so far off on my odometry that I'm not measuring something that's perpendicular to the walls, or the walls are bowed. And the course I have at home that I made, I screw a 1/2-inch piece of plywood over. I made corner pieces, and I screw a 1/2-inch piece of plywood on there. I can measure that step in the plywood. So, one thing that I have found though, because one of the things I'll do, and I'll show you, that's part of the code too, that as I'm going through the goal of the course, I try to say, okay, is this the 35 inches? I think it is. And then I'll actually update my Y value based on that as well. But I don't always get that reading. It doesn't always come through because the travel of the robot, it may be in 2 consecutive scans, so it's not 100% reliable. All right, so this is their little frame grabber app that they have. And this comes with, actually there's a software API as well that you could write application on a PC that use it. And this is basically just their front end for that. Hopefully it won't break.
Close anymore.
Did you actually buy a Kyle license?
Oh, I work in Kyle
Oh,
constantly
yeah.
at work.
Yeah.
Whoa.
Yeah.
What's that?
It's an IDE for embedded,
Oh, is it?
very much for embedded.
Why do you have so many serial ports? Is there something attached?
It's when I use the USB emulators all the time, and then Windows it'll click off one after another. Yeah, when I plug in a new USB, I think I'm up to 56 or something, COMS 56. So, all right. So here we're actually taking readings, and you can kind of see. You see these right here? That's me moving around. And like I was saying, here, let me move out of the way. Maybe it'll pick up the wall. See, this would be the wall right there in the back, right? So if I rotate it around, and see, now that the robot's facing the wall, you can see the wall is at 90 degrees because that's what I was saying is I have that device rotated 90 degrees. But you can also see that you're not getting scans from everywhere, right? So a lot of times that can either be that something's out of range or that you don't get a high enough quality level out of it.
What is your little red line that?
I'm not sure what the red line is, to be honest with you.
Current something degrees.
It may be
What is
the
it?
longest vector.
Hmm.
Right. So, and you can see me stepping back right there. I think this is going to be clay right here. So, like I said, the data is not always that crystal clear. If you have, again, in our CAN environment, it's very easy because the walls are, it's very defined. But that gives you an idea, like, I'm standing right in front of it now, and it shows me as a V there.
So that water bottle, that will show up. So you see that?
If it's tall enough, it will.
Yeah, unfortunately, it's probably going to show a lot of us as V's.
Well,
So what was the minimum range? How about this? Well, I'm going to say a lid. Would that be a good thing to show?
well, you cocould do something like
Depends on how well it
this. Where,
reflects.
But you said you don't use that to find the cans, only to find the walls? Or?
right. See, now you can see my laptop on there. That's what that line is. Right?
I don't know if we're out of range or not.
Well, I mean, it's obvious that even some things that are in range
Yeah, they're out of range.
don't really pick up that
Just a
well.
dot there.
Right there. At 240 degrees.
I have both.
So this is at a high baud rate and it comes back. It's just one-way communication.
No, you send there's a couple of commands you can send over there to start a scan, like to turn the motor on. You can turn that on and off. That's one of the commands you send over to it. There's like a reset command you can send to it. If you start getting a lot of failed samples, that sort of thing. I really haven't had any trouble with it. Once you get it spinning, I mean, it seems to feed you data pretty regularly.
What is the market?
I want to say 57.6. I think it's adjustable. I think that's one of the commands you can send it. And I think I just left it at the default, which I'm pretty sure is 57.6. So in order to, and it just pounds data constantly. So, it takes a little bit of CPU resources. That's why I do it all in an interrupt. I just let it run in the background.
Yeah, when you showed us the data frames, is it binary packed kind of, so many bits for range, or is it ASCII? And not to worry.
I put it in a unsigned UNT16 array.
Okay, so it fits at 16 bits.
I don't remember how the serial data comes in. I think it's just not really, well, it's not ASCII, but it's, you know, binary representation
Right.
of a 16-bit number.
Okay, okay.
So,
Like,
I mean, it doesn't come out as ASCII now.
okay, probably like, what, 9 bits for the angle, and like you said, 3 bits for the quality, stuff like that.
I don't remember.
Yeah, all right.
We can look and see.
Yeah.
It's,
See it there, 210,
Doesn't pick us up, doesn't like the zero thing at all.
need a fatter table leg.
yeah.
It's just sometimes, but not always. So it looks like it must not have overlapping beams, overlapping spots, because you can pick objects that aren't caught. And usually, like, we learned this, I did laser rangefinders professionally in the 80s for defense tanks and stuff. And the whole idea is that things like wires, since they're round, there's always a perpendicular surface to the beam. So you don't have that wall problem where it glances off, because there's always a perpendicular surface no matter what angle. So like on our systems, the beam would be so wide, the way at 10 clicks, 10 kilometers, and it was so sensitive that we could pick out power lines and stuff, you know, kilometers away.
Wow.
So this thing, just because you can see it's unable to.
Well, you got to make sure it's at that level too. There you go.
So let's find me. So this is me, right?
Yep.
This is
Around
me.
210.
I'm right. I'm right
Where
at
are you?
210.
Okay. Yeah.
See me move?
Yeah.
Yep.
That's me around
So
210.
this is
Okay.
Okay.
So if I take this thing
Put
and
it
flip
really
it,
close so we can
See
see
that?
it.
There's the dot right there. You can kind of see it a little bit.
see it shows up every now and then.
Should
Well,
be
it
in
would
front
be,
of
it
you.
would,
Yeah,
yeah,
it should be in front of
here.
you.
Yeah,
Close
see, there it is.
Yeah. So it's showing up every now and then. So there's a gap in the display pattern. Then.
Yeah, I
So-
wonder, later, maybe, Doug,
Does that make sense?
does your camera have IR? We could switch it to IR mode, turn out the lights, and could we see the spots?
I don't think it is IR, but
Okay, well,
this
okay.
camera's not that.
Okay. Something to try. Okay.
And you know, what you're saying, Carl, about that, one thing I found was, like the time of flight sensors,
Yeah.
like the ones that we had.
Steve Micro and the
Yeah.
tiny LiDAR.
They seem to average things. Like, for instance, I had the time of flight sensor set up, and I had it looking through a hole in a piece of cardboard,
Yeah.
right? So I could adjust it so that it went straight through the hole in the cardboard. But as I took an edge in the back of the hole and I started to, include it in that gap, what I expected to see was almost an instantaneous from 5 feet or 10 feet or whatever to what I was sliding. And what I saw was this gradual change until finally it said, okay. And what I surmised from that is that it kind of takes an average. So as you start to hit its field and it starts to get some sort of reflection from its time of flight, it kind of averages the entire range, is what it seemed like to me.
That's exactly what happened, because we looked at the patent and the stuff on the spec sheet for that. It's basically, he's talking about, there's a sensor in iPhones. It tells how close it is to your ear, so it can turn the volume down. Actually, so there's a laser rangefinder in my iPhone right now. Believe
Well,
it or not.
they use the time of flight sensors for your thumbprint too, because a lot of them will do color hue, and they're sensitive enough to actually pick up your fingerprint.
The print. But what they're doing is that it's actually sending out many pulses of light, and that little sensor in there's average is counting the number of photons in bins. So that's where the averaging, because it is literally an average of photons in different bins.
Right.
So I wonder if it's the same kind of principle and patent on this one or a different.
Yeah, I would presume since it's
not
very
one pulse per degree.
Because when we did it in the military, it was exactly one pulse.
Oh, it was?
It was exactly one, because we would charge up, like on the gas one, we had a cavity that was a foot long, all right? It was this really pure CO2 gas, highly polished infrared lenses and electrodes. We would charge a capacitor up to 20,000 volts, and we used a thing called a spark gap as a switch, so it would go from 0 to 20,000 volts across the CO2 gas in about 100 nanoseconds, which meant it went from like mega ohms to 10 ohms, the gas did. So it went from 0 to 800 amps in 100 nanoseconds with a 12-foot loop of current. So imagine the EMI on that. right? But that was a single pulse of light that it would do, and that's how it would send out. It was only 100 nanoseconds wide in time, but it would send out a single pulse of light at 200 megawatts. And then it could detect the microwatts after it goes down through atmospheric attenuation and
That
smoke.
wasn't a weapon. Sounds like a weapon.
You wouldn't want to get your eye in front of it. We actually focused it by taking Polaroid film on the table, and it would blow the surface off. And that's how you could know if you got the optics focused down to a dot.
Yeah.
But it wasn't the weapon. That's not the kind that they use on missiles. That's a different.
Not
The
Star
Exemer. Sorry.
It's like a plane size laser.
Lasers are fun. I spent too many years on it. Sorry. Sorry.
All right, so now we're gonna start talking about how I actually implement this, specifically for the CanCan contest, specifically on CanMan here. So this is one of the ones I mentioned earlier where I try to measure where I'm going through the goal right here. And this is actually the code that I use. And this LiDAR DAT is the array that I was referring to earlier that gets updated through the interrupt function. And again, here's the angles that I'm passing in. Now this kind of looks funny, but really what this is in my robot, and if you ever read David's documentation online about, you know, the outdoor contest and driving the robot, everything to the right as a robot is a positive number, everything to the left is a negative number, right? So as the robot's running, think about it, a line here, so anything over here would be a negative 1 degree, 2 degree, 3 degree, all the way to a negative, 179, and then positive on the other side. So what I have to do, since my LiDAR data is 0 through 360, then you have to convert it, right? So that's what I'm doing here, is I'm getting the angles that I want to convert. And when I pass this base angle in, I've already taken and rotated at 90 degrees, right? So I know that, and again, in the example I was giving earlier, if I'm at 45 degrees here in the course, then I'll pass it, I pass it 90 degrees. And we can look at that code too. I got to apologize, I hadn't looked at this. It's been sitting on the shelf for a long time. Until 2 weeks ago when I got the email from Doug, hey, can you give this presentation? So,
Right.
Yeah, I think that was me, but that's right.
Right, okay.
So base angle is
Doug and I
relative
look
to the
alike.
course.
Right, in other words, I've already given the offset that I want at the 90 degree. This is the angle that I want to read, right? That's what I'm passing in here. This isn't necessarily the heading of the robot. It's the angle that I want to read the width of, right? Which is based on the heading of the robot. And then I have to convert it from bipolar angle to 360, because you can't just say, okay, I want to add 180 to it, right? Because if you're depending on where you're at, and David explains it much better than I'm doing here, as far as converting this from a bidirectional heading into a 360 degree angle. And then it's just a simple matter of getting the two distances, adding them together and converting it into inches.
So what you're returning there is the width of the
Like a
doorway.
perpendicular width.
Right. And so in this particular situation, I'm looking for this to return me a value of 35 because that's the width of the goals on the course, right?
So I guess you could also look at the two opposite ends and figure out, okay, that's got to be 10 feet, right? Or
You can do it, there's a lot of things you can do, like,
yeah,
because one of the things that I do is I detect the angles of these edges. Because at one time I was thinking, well, kind of like what you do is you scan the course one time and then say, okay, here's my edges, I'm gonna go between those.
yeah,
Right, it doesn't matter what my odometry says,
right.
but you don't even have odometry on that.
I do, but I don't use it to find where the goal is. It's kind of like point and shoot, you know, line up and go straight.
Yeah, I kind of went around a little bit about, you know, where or how to use it and what was best to implement. And it turns out, you know, I only do a couple of things with it, is what it really boils down to, is I try to detect this, and then that way I update my Y value in my odometry based on, because I know if I start here and this is 0, right, then I know this is 120 because it's a 10-foot course, right? So you got 120 inches in a 10-foot course. So if I detect that this is 35, and I think I also make a determination that I'm within a certain heading, because you don't want to be right here and think, oh, that's 35, right? So you're always trying to filter out data that doesn't jive with what you want to do.
So are you calling this all the time and then to see when you're in the gate, or do you just call it when you're in the gate to measure the width of the gate?
Now you're testing my memory.
Okay.
I think I have one of the, in my behavioral sequencing, my behavioral stack is really what it is. One of the behaviors there is run to goal. So I'm pretty sure I just test it when I'm in that state.
When you're.
Because I know that I have a can, and I know that I'm trying to score a point, basically, run for a goal.
So you turn it on then to find when you're at the threshold of the goal?
Right. Or that's when I start testing to say, is this 35, is this 35, is this 35? And if I get a yes, then I know that I'm going to update my Y value.
Okay.
I mean, we can look at that if you want. I can bring up the code. It's a little messy, but I had to clean this up for public consumption.
Doesn't
Yes.
it also correct your theta, now that you know what square is as you go through that?
I guess you could, but again, it's just not that consistent. And I've got the function in here where I align to the wall and then adjust the
You do that.
angle.
I see, not at this.
Right, yeah, not here, that's a different function. Because I used to not have an IMU on this robot, and then when you gave your presentation on the Bosch 55 or whatever, I gotta have one of those. So then I have one of those on here now, so my heading is pretty accurate. I mean, those Bosch sensors work really good.
How do you talk to that? Do you talk to I2C or serial?
It's either I2C or SPI.
I think it's SPI, yeah.
Is it?
Yeah, I think so.
It may do either one, but
I think it even has this.
So it
UART
doesn't
on
drift
it.
very much on your heading?
no, the thing is
Calculation.
rock solid. I mean, you
Okay.
turn it on and then that's 0, because I have the magnetometer turned off, right? Because it's actually on the bottom board here that's not too far from the motors.
Yeah.
So I just turned the magnetometer off, like the Iron Rain people showed.
Yeah.
And so basically you just have to be cognizant of when you set the thing down that it's straight. When you turn it on, it's going to say, okay, the IMU, this is 0. This is my 0 heading. So if the robot is not facing to what you want 0 to be, then bad things happen.
Need a good fiducial mark on the floor.
Yeah. Actually, I thought about putting like a little laser pointer on there.
Oh, yeah.
And then line it, especially like for the quick trip thing, lining it up. Okay, here's the laser pointer.
That's been done.
I've done that.
I've done that.
Okay, so now we're going to talk about the finding center, which is one of the more useful functions that I use this for, because your odometry just seems to always creep. And of course, with the can soccer, and you may bump into somebody, then things go south in a hurry. So what I try to do is, the function we're fixing to look at, is I return what the error is to center. In other words, like right here, and again, I said everything to the left of the robot's a negative number, right? So in this situation here, I would have a negative, 10, 12 inch error that this function is going to return to me. That's what I'm trying to do, because in the behavioral stack here, one of the things that the behavior is responsible for is what the heading error is. In other words, from where I'm at, where do I want to be? And that's the heading error, and that's how you steer it, right? So in the behavior, I can set the heading error to a negative number and it'll steer left, and I can set it to a positive number and it'll still steer right. So that's why this function is going to return the value to center, not necessarily find where the center is. I guess it would find where the center is depending on how you want to think about it. And this is how I do it. Again, this is just converting the angle that's passed in, because again, it's got to be relative to the orientation of the robot now. Right, so I can find, even though I might not be parallel to the center line, I can still find center no matter what position I'm in. And that's based on the angle that passed in. And then this is similar to what we did, I find the two distances. And then I have this function that I use quite a bit. It's kind of like fuzzy logic. I called it kind of equal. And what I can do is I can pass two numbers into it and then pass a third number in it. And if these two numbers are within this range, it returns a positive or a true. So, because, anytime in robotics like that, if you say, well, it's got to be dead equal, and you're dealing with millimeters here, it's never going to be dead equal, right? So this is kind of my way of generating some fuzzy logic to say, okay, are we kind of equal? Are we good here? And sometimes this number here can get pretty big, depending on the slop you want in the decision, right? So basically what I do here is if I'm within 30 millimeters, which, a little over an inch, then I just say, okay, we're good. We don't need to do anything here.
You can call it bocce ball and grenades routine.
Yeah.
Close enough.
Or if we're further out than that, then I go ahead and I calculate where the center is, which is basically just the difference in the two distances, and I take the average of it, right? And then, of course, I convert it back into inches. And this returns a float, so this could be a decimal number. Because by doing this, you actually do, if you didn't return a float and you were just doing integer math, you'd lose quite a bit of resolution there.
So this is just the distance off in one of the two directions, just in that it says this is distance from our current X position.
Well, here, I'll go back to the drawing. Okay, so to explain this a little bit closer, this is the one distance that we have, and let's say it's 20, just to make the math easy. Okay, and then this is the other distance we have, and let's say that's 40, okay, just to make the math easy. So the difference between those two here is going to be 20, right? So half of that is going to be 10.
So
Okay, does everybody follow that?
Yeah.
Okay, so at that point, what we've done is we said, okay, this line's 20 millimeters longer than this one. So if I move 10 here, right, notice the distance here. So now I'm going to average the distance, and then that's going to be, because if the two were the same, then I would be at the center, right? So that tells me that what the difference between the two lines is going to be, half of that's going to be where I'm at to where the center is. Does that make sense?
Yeah, so what my question, that got the distance to those two walls. Do you orient to the other walls or do it to the long walls too, or just to the
No,
side?
I just do it in the X value
Okay,
because of the openings on the ends.
okay.
And that's why I was saying earlier is at one time I was detecting these edges and trying to, use trig to triangulate.
Reorient, yeah.
Because ultimately, if you really wanted to, you could do away with the odometry and just orient X and Y based on, the points there, the width here. You could even do your angle, your heading angle, as long as you didn't get spun all the way around based on these edges here. But you know, it was one of those things I never got working the way I wanted it to, and then the sensor came along, and then I just used it.
You didn't have to.
Yeah, I didn't have to. You know, it got really hard, so I gave up on it.
Yeah.
There was an easier way.
There's an easier way, yeah.
Easier, just throw hardware in. In that, that kind of assumes that you're perpendicular or parallel to the long edges, right? Because if
Yeah.
you're slightly rotated, you're 90, you just look at one reading, one 90 degree or two 90-degree readings.
Now, this angle right here is the angle of where I'm 90, the angle perpendicular to what my heading is.
Right.
So what I do is I take my heading and I subtract 90 from it, and that's
Okay.
the value that gets passed into here.
Yeah.
So no, it doesn't matter whether or not you're parallel to
Rotated
the center
along.
line or not,
Yeah. Okay.
because it knows, like for instance, if the robot was angled, then it knows to use this sample and that sample,
Right.
and not this sample and that sample.
Right. Yeah.
And that's
So-
that's the whole idea behind the base angle is put it in a frame context, you know, an environmental frame context,
Yeah.
right? So, and I used to do this, I would run this function when I picked up a can. So you could be at whatever angle
Mhm.
in the 360-degree type of thing. And this is, like I said, this is probably the most useful one that I have. And as you can see, it's not really that sophisticated. It's a little confusing once you look at the data. And also, if you notice here, you're going to come out with a polarity, if you will, because distance 1, if it's less than distance 2, you're going to come out with that negative number, so you're going to turn to the left. Right? And in our example here, this angle 2, see, I'm rotating all the way around 180 degrees. So this angle 2 is actually the angle on the left, or the distance to the left of the robot. In other words, this would be angle 2, or distance 2, and this is distance 1, right? So in my example here, distance 2 is greater than distance 1, so I'm going to come out with a negative number. You know, in the example I was giving, right, it was 20 minus 40 is going to be 20, and then divided by 2 is going to be 10. So it's going to be a negative, or minus 10 millimeters to the center of the course.
So Scott, to understand what you do with this number, do you use that to offset your position, or what I hear you saying, what I think, is that you basically use that as a steering because you're trying to steer toward the center to get to the goal?
Actually, both.
Okay.
And we, actually, if I have time, I'll bring up some of the code and I can show you. So actually I do both. So the heading error now is based on that value. And also I update my X value based on that reading, right? Because that map looks a little funky because you have to take the entire course and then subtract out of it. But I can show you
And
that.
one more question on the previous picture where you take the measurements. What would happen if there was a can in the way in between one of the walls?
It doesn't matter because this is above the can.
Okay.
It doesn't see the
That's
cans.
Great.
The
And are
walls.
you still when you do this, or are you moving?
It doesn't matter. I can do it on the fly. I think practically though, as far as when the software is called, I think it's after I pick up a can.
So you are still.
Yeah.
It seems like.
Because basically I want to know, okay, I'm fixing to run to the goal, so I need to know what my orientation is within the center of the course, because I don't want to run towards the goal and hit the wall, right? Thinking that I'm too far over or not centered. And if you've seen the contest, I almost always end up right in the center of the goal, and that's why. Okay. So now this is one that is fairly simple as well. And basically all you do to find the edge is look for 2 consecutive samples with a distance value that's greater than whatever you want to, whatever value you pass into here. And basically I have this non-volatile array that I keep all the parameters that I can go in through the terminal and adjust things. That's what this NV adjust value is. So basically I can go in, I can set this edge limit here to whatever I want to through the terminal interface. And then basically all you do is you scan through the data here and, well here, I'm sorry, here, well you're scanning through in this for loop. So here I'm using my kind of equal function again, but if these values are outside this range, basically you got the knot going on here, then I say, okay, I found a step. So I'm going to log that into my edges array, which is this array here. And when I was looking back over this code recently, I thought, because all this is doing right here is I'm determining which angle to use in my edge array. But then I got to thinking, well, it doesn't really make any difference because those two samples are side by side. So, and what I do here is I say, well, whichever one's the lower value, then I use it. In other words, that's the angle or the sample that was right before the edge. Does that make sense?
Yeah.
Is that confusing?
Okay.
It's really not needed because it's going to be, 59 or 60, whatever the number is.
Right.
So it's really not that needed. But then I can scan through this edges array and find out at what angle my edges are at, right?
Okay, say, the goal's set up here and there's nothing out in front of it, nobody's standing there or anything. You're not gonna get a reading for it because it's probably too far, right? So do you also have to look for that situation where you've got valid readings and then nothing because you're not getting a reflection back, it's too far? Did you ever get into that situation or?
Now, I see the problem that you're talking about.
Yeah.
And that would absolutely be affected by whether you set it to a minimum value, maximum value, or leave it alone,
Right.
right? But I don't, like I said, in practicality, I don't use this in the contest.
Oh, you don't?
So I don't,
Okay.
this was something I was trying to use originally. And again, this was before I had the IMU on there. So the idea here was I could update my theta based on where these edges were.
Yep.
Right? Because based on where I am in the X and Y and the odometry grid and what angle those are is it's cosine or whatever it is.
Yeah.
But in practicality I ended up not using it. So yes.
Just throw in parenthetically that edge detector mechanism is the way the SRO4 sonar finds CAN.
Okay.
And then
Yeah, that's right, because you scan.
Yeah, so
Okay.
basically I'm scanning 360 degrees, which is two sonars. But if that could actually see the cans, then you can use that step detector to tell you where the cans are.
Yeah.
And you'd also know, because you know the distance, that those are not walls, that they have to be cans or opposing robots.
Well, that's true, but you would have to look at the data a little bit closer to say, okay, well, I've got this one sample that's this close, and I got all the other samples that are back here, So, yeah, I can see what you're talking about. I try to stay away from really complex stuff like that. I'm just a simple programmer here,
Simple country program.
Just a country bumpkin programmer. I'm not an academic or nothing like you are.
One of the things that, in using that, the course, especially if we set it up right here, there's a pretty bad hump in the floor, and it would actually make a little gap between the two boards in the center of the course, and it would use that as that first reading where there was a transition.
Oh, would it?
Yeah, it would catch it.
I've seen that with the sonar also.
Yeah.
It sees that crack in the wall and says, there's a can.
Yeah.
I've seen that.
Yeah.
See, so it's a good thing I didn't use that
You
method.
were
then.
dead
Don't use that
down
routine.
garden.
Yeah. Well, the cameras have their own issues with the color hues and the
Oh,
lighting
yeah.
and all that, so,
Wish it could be like our eyeballs, but they're not.
yeah, well, it's only, how much are those cameras, 50, 70 bucks?
Yeah.
So,
What it costs for an
what do you
eyeball.
expect? All right, so here's the line-to-wall routine, and I have to apologize if anybody that's very astute would would realize that according to Doug's blurb, which I was blown away by how much he was pumping this up. One of the things I sent him was which one of these functions I was going to cover. And one of the things I told him was an inside edge, because at one time I was trying to write an algorithm to detect the inside edge here.
Yep.
But when I looked at the code, I went, oh shit, I never implemented that. So it's ominously absent in this presentation.
Oh, that's.
So I'll apologize for that now, and then it'll never be spoke of again, right?
Okay.
Okay.
But that is a good thing though, because if you have those 4 points, you pretty much have the whole layout and where you are.
Well, you know, I sat down the other night when I was putting together the presentation and said, oh shit. I tried to throw an algorithm together, and I was like, I'm not going to put up an untested algorithm in front of this group and get slammed like, well, this isn't going to work that way. You know it. So I just,
Who would do that? Who would?
yeah, no, Ron would.
No.
All right. So aligning to a wall, we use 3 points, whereas basically up to this point we've only used 2 pieces of data. This time we're using 3 different points. And what I do in my algorithm is I use 15 degrees. So you have each one of these thetas here is 15 degrees. So of course if you're square to the wall, the distance on those 2 should be the same, right? And to verify that you're not hitting here, or you know, I take the length of this, and that's the cosine of the length of the other. All right, so if we look at that code, you have the, up here at the very top, these 2 angles, you know, 75 and 105, that's 15 degrees on either side of 90, right? And in order to call this function, I'm positioning myself what I think is square to the wall at 0, right? So that's why there's not an angle that's passed in here. And that's also why I can take and just say, okay, I want 75 degrees and the value at 105 degrees, and what are my lengths here? And as you can see, I pass in 2, so it's got to be within 2 millimeters of each other. You know, so that's pretty close, that's pretty damn accurate. So all of this right here is just the updating of the headings, because this function gets called repeatedly. In other words, when it gets into this behavioral mode, it's a repetitive call until this function returns a true, which means it's aligned, which I think is, yeah, well, this is abbreviated version, but this is a state machine. So basically, once I increment this state, the next state from where I cut and pasted this out of is to send a true back. So you have to remember, this is being called over and over and over again. I think it's every 100 milliseconds or some crap like that. So basically, now we found out that we're not in alignment, so we fall down through here, and I check my headings so to determine that I'm close to where I should be. And then this right here, and here's where this BA, which is behavioral array, and it's at index waypoint, because this function happens in the behavior that I call waypoint. Because originally I used waypoint to that behavior to like rotate towards the next heading that I'm going to, but it kind of turned into a generic bucket for things like this, so that I didn't have to define a separate behavior for it. And that gets into more than what this talks about. But this is basically how I'm steering the robot. So depending on the difference between these 2 values, I rotate the robot based on that value. So the further away from that it is, the harder it's going to turn. And basically I have this other clip function that I call so that I can limit how much I turn, you know, because you don't want to oversteer it. So I limit that. And this is where I'm calculating, this is where I cancel out. In other words, if I can't seem to get into alignment, then, and again, this timer value is something that's in the rest of the function. So this is where I cancel out of it if I can't. Because if the wall is kind of crooked, then you'll drop down into here, and like I said, it's the cosine, right? So instead of just calling the cosine, I just have the constant value here. So here's where I'm determining whether or not this is within range and the wall is straight. In other words, basically this is telling me that that center vector that I showed you on the print on the drawing here, that the length of this vector here is in fact the cosine of one of the other vectors. And then that tells me, because if the wall was crooked, right, I could have the same length here, but this would not be the right length. And it's that kind of triangulation that you can really use this LiDAR, that's really where the power of it comes in at, is being able to triangulate things, because you have so much data to work from.
Okay, say that again. So if you're rotated, it's not going to be the cosine? Why not?
No, if the wall is not straight,
Yeah, straight.
or it's got a bend in it or a
all
bow,
Yeah.
then this length is not going to be the cosine of that length,
Yeah. Okay.
right? And if you're not square to it, it's the same thing, because you're expecting this to be a right angle here, right?
Mhm.
That's the idea.
So isn't there easy, am I missing something? Why not just look at, what's the shortest
Yeah,
thing?
distance.
As you
Yeah,
scan
that'd
through
be
like half of
perpendicular
this,
distance, right?
half of the scan, the shortest ping will be
Perpendicular.
Angle.
perpendicular, and
90,
then you'll know from whichever angle that is, the orientation of the robot with respect to the wall.
What if you were over here, and so the shortest ping is here?
You gotta look at neighboring pings.
Or
Yeah,
keep
because
track of history.
if this was over here, right, and so my 15-degree angle was pinged here, and my other 15-degree angle is pinged here, but then I try to rotate around so that these two are the same, right?
Yeah.
I'm not going to be square to the
Right,
course.
right.
Well,
And the test that this is the cosine of this will fail.
Well, I think the simple description, if I can jump in, what you're saying would be true with an infinitely flat wall.
Yeah,
but you could look at that.
But the problem becomes when you're in a corner.
when you get close to the
Right.
corner.
But so you need
Yeah.
to study your intermediate pings in that case. You'd need to look at that sweep, right? Go ahead.
If I understood what you said, it's very insensitive. You said you sweep around, and when you come to the minimum, that angle is at right angle.
Yeah.
But it's very sensitive, because if you're off just a degree, there's almost no change in distance.
Right.
It's like if he were to reduce his plus or minus 15 to plus or minus 5 degrees, it would be very difficult or not very sensitive. And so that's basically what you've done, is reduce it almost to zero.
But with this method, because he's looking out further.
Yeah.
Yeah.
Well, I actually started with 30 degrees here and had problems because, again, when I was calling this was when I picked up a can, right? Because I wanted to orient myself before I drove to the goal, then I was trying to orient myself. So the robot could potentially be anywhere on the course. And then you'll run into these issues where you're hitting these walls. And actually, even with 30 degrees, I was hitting these walls quite a bit. And the other thing with the shortest distance is you would also have to, say you were over here, you would have to recognize, oh, this is the left-hand side, not the right-hand side, right? I mean, it's the same algorithm, but you would just need to know, because if you think about it, you're trying to orient yourself in space. So if you were over this way and this was your shortest reading, but you were expecting it to be to the right of the robot. Now you're going to align yourself going the wrong way, right? So, I mean, I'm not saying that this is the only way to do it,
Yeah.
but this is how I did it.
Yeah, I was just
And
wondering.
I have to say, I have to basically iterate it to the same point Scott
Did
does.
you-
I do it with sonar, but basically, I've come to the same conclusion.
So has anybody tried the other way?
What mine does, if I can jump in, is since I've got only two data points, is that I first look to find where they're both the same length, which I do by rotating. And then once I find they're both the same length, then I do basically a little short rotation to see that the wall is flat and then I'm really normal to it, which is because I don't have those extra points.
You don't have that third data point.
And so you can run into a situation, imagine, well, if you're 45 degrees off, you really can't get back on it, because you don't know which wall is.
Which one is which?
Which
Right.
which one is right. So you have to start with the assumption that you're not going to drift that much.
So, question. I asked the question about what if the can was in the way, but you're above the can? But isn't there another robot out there? What if you got a measurement to the other robot instead of a wall?
Well, that's why all this qualification's going on here, because everything, once you drop into this area here, all of this is looking to see that, are we really valid here? Is this really what we think it should be, right? And if you can equate those three data points, then, you know, in this algorithm, then you have a high enough confidence that you're gonna update your values. And like right here, this is what I was saying is this updates my location X value based on the width of the course, you know, minus how far I am from the other side. You know, 270 would be the left-hand side in this case. And then I convert it back to inches. So I basically just set it based on this LiDAR data now that I know I'm square to the wall. And then if I'm turned the other way, then I use the other angle, 90 degrees. And that's what all that's doing.
And if at a certain number of iterations you can't do that, you give up, right? You say,
Yeah, that's what this
I
timer,
just have
this
to
right here is. Basically, we haven't satisfied, these two 15-degree angles aren't within 2 millimeters of one another. So as we drop down through here, and actually every time this function's called, this value timer gets incremented on every call. Right, so I know how long I've been in here.
And are you still using this aligned to wall with the LiDAR, or
No.
do you use the IMU now?
I just use the IMU now. Because the other thing is this took quite a while, because you have to, you know, creep around, and it would, you know, kind of, eventually it would level out and it would settle in and say, okay, we're good to go. But it was also very sensitive to the wall being crooked, and you know, our course gets bent up and crooked all the time. So I didn't really need this update because basically I'm updating my heading as well here, right? Whether I'm going 0 or I'm at 180, depending on where I thought I was to begin with. So I don't, like I said, the IMU is so much more accurate that I don't even have to mess with this anymore. Okay, that's all I had for the presentation.
I have a question.
Yes.
You were showing us the live display a while ago.
Uh-huh.
Can you set that down over in a corner where we can see, where it can see a whole corner so we can see what that looks like?
Sure.
We can make a corner out of tables. or
Okay,
something.
I will say this. There is, just so everybody knows, you may not recall this, but when I did the presentation on the Bennywick LiDAR, the second part of that presentation was data points taken on the CanMan course for center, starting, and corner. And those data sets are out there on our website, and it can show you some cool things. So I'm just
Maybe
saying
make
that's
a corner out of
available.
this.
There you go.
Yeah, or I could set the box on its side and use the flap.
Yeah.
Or you can do what Jason did, is just stick the box over it.
Yeah, that may be too close.
Too close, yeah.
Oh, wait a minute.
About plugging it in.
Yeah, the
Yeah,
old
plug it
plug-it
in
in
and
trick.
Again, darn electrons don't know when to jump.
Yeah. Well, isn't that what Wi-Fi's about? Okay, yeah, see there, you can see the corner we've got set up right there. Like I said, if you have a nice, flat, straight edge, it picks it up very well. But once you start getting, you know, odd shapes and whatnot, then it really doesn't do a very good job. And you can see how that would rotate and you can see that now that I'm pointing straight at it, you know, that's 90 degrees to the LiDAR because I mounted it on my robot. And you can actually see the back edge of the box. Yep. See how you have this is the front corner of the box right here. So it's actually, even though the box is reflecting, you know, the IR or the pulse, you would think it, you know, would have poor reflection, but it picks it up fairly well. And then you can see the wall in the back, and then you can see me right here.
So if the box was a mirror, it probably would, it wouldn't be able to, you could make the
Right,
box
yeah.
invisible to the LiDAR by making it be a mirror at IR. Yeah,
I don't know, I've never tried a mirror. I mean, I would think that you would still have a reflection of the light, depending on the frequency.
Depending on good, on how diffuse the surface is. So the diffuse surfaces, they have all these little nooks and crannies in practice. So there's always some bit of the surface at the really like microscopic level to reflect the light. So if it's a perfectly, I think specular is the term, so it reflects everything, then it'll be invisible.
Yeah.
But since it's a diffuse surface, because it has this texture to it, and that's why when you go, you look at these military vehicles, and you see how like the F-111, they have these very sharp, non-90 degree angles with a
Right.
very small knife edge. That's because the obtuse angles, there's no 90 anywhere, so it's always going to reflect the radar off some other direction,
Right.
except for that one thing that looks like a curvy edge where there's always a flat surface. So the smaller, the better you can make a super sharp knife edge, the less reflection you get. That's why they're invisible to radar.
I can say that those sharp infrared distance detectors that don't work pointed into a mirror, they return maximum distance pointed into a mirror.
Yeah.
So if you wanted a LiDAR stealth robot, you could make a mirrored, you know, shell on it. So.
How about a mirrored contest course?
Or that, yeah.
Evil, evil.
Navigate through the house of mirrors. at the
Yeah,
end.
multiple
No.
cans and multiple
See,
robots.
Dave's only saying that because he has sonar,
That's just me, yeah.
and the mirror is only in the optical wavelengths, not the
Actually,
audio.
that's
Yeah.
not true. Shiny surfaces tend to bounce
Do they?
the sonar away.
Yeah.
So like if you scan along a surface, when you're looking right at it, you see it and then it goes away and then it comes back.
So it's a broad spectrum reflector.
There you go. We need a black bot.
Yeah.
Cool.
Well, Scott, you said they don't make this one anymore.
No,
I don't think they do.
They do.
They have a newer model that doesn't have this basically is just a little O-ring that runs on the motor that drives the thing, and the one they make now, I think, is all
Kind of
just a
integrated.
round
Yeah.
module.
Scott,
Oh.
but they do make this model.
Oh, do they?
Yes, it's colored development kit, and it's $99. You can buy them all day up at Robo Shop, Canada. I don't know if Tanner has them. And
I think so.
they have improved it probably from when you're Scott, because I got an older one too. I got one of the first ones that came out. And
Yeah, this one hadn't been out long when I got it.
and but now they've sped them up. I think they might be 10 hertz now. I'm not sure. And they've done a few other things to them, but it's just $99.
There was a little board that James made.
Right.
He sold a whole bunch of them.
Mhm.
That-
What did that do?
That was for a similar LiDAR fact, very similar.
Out of the Nitos, yeah.
That goes off of a Nito robot.
But
And there's
this
also-
doesn't require that.
It probably has that.
This one
built in.
has, there's a little, it comes with a little serial port board.
Yeah,
But I
it
don't know
has
if
this-
he's using
and that's
it.
what I'm using here. There's a little USB to serial board that also turns the motor on.
Yeah,
And that comes with it. So I'm just using that so that
Yeah.
I can show it up here.
yeah.
Um,
So.
Yeah, James's board actually used to, it was a closed loop control
Yeah,
over the
pin
motor
controller,
speed.
yeah.
Yeah. That was,
So-
so if you look at his board, what he has, he hooks up, he uses the serial port. Because, just like this one, that's a serial port at 11.5-200. And then he also has a MOSFET on it, which he used to drive the motor, because it's only going in one direction, so he doesn't need a bridge. And
I think he also did some serial formatting of the data.
No, that's his software. That's all software.
But he had that in that chip, didn't he? I thought he did some formatting.
No.
No? Okay.
I mean, you buy the LiDAR unit off eBay, you get what you get.
Did it have a teensy on it? Is that-
Well, he's updated it now to, I want to say originally it was a teensy,
LC, I think.
the
Low
original
cost.
one was like a teensy 2, which is kind of like an Arduino.
We should probably define terms like that for newcomers.
Yeah, well, it's a line of chips that's made by a gentleman you can just write teensy and it'll pop up. But it's essentially, it's an ARM,
PRJ.
depending on which one you get, M Cortex series chip that runs in Arduino mode.
And it's on a board about the size of your little finger.
Right, yeah. And that's why it's called a teensy.
But now they make one that runs at 600 megahertz, same size,
Same size?
same price,
Does it
roughly
require
$30.
A fan?
Ron?
No.
Is that a TT on?
No, that's an LPC.
Yeah, he's
1768,
just
whatever
released a Teensy 4, which for $19, which has an M7 on it.
James
Yes, sir.
who?
Yes, sir.
James who?
Huh?
James who?
James, our ex-vice president. James.
Yeah. James is
Laurel.
Get Surreal.
Thank you.
Is his website, getsurreal.com.
I think he still sells them, right?
Oh yeah, and he's updated it too. Like I say,
Oh, I didn't-
the original one was a Teensy 2, and now I want to say it's a Teensy 3.6, but I might be wrong.
Yeah. Oh, speaking of which, I don't know if you saw, I sent out around a thing, there's an F401 based, it's kind of like the Blue Pill form factor board you can get from Banggood now. So it's not only whatever it is, the F103,
Yeah.
it's an F401.
All right.
So,
Okay.
and it's like, they were like $4.
Wow.
So.
All right. Hey, Scott, I don't know. It seems like the question and answers has drifted off away from LiDARs. All right?
Yeah, that's fine. I've talked enough.
Okay. So, everybody?
So right now, you're just using that to find center, and all other guidance is the B&O 055, or?
Yeah, well, I use it to find the center, and sometimes it finds the goal, the opening.
Yeah.
Scott, if you get hit hard, your robot got clobbered in the competition. Okay, what do you do? How would your robot respond to try to recorrect itself?
Well,
Doesn't the IMU take?
the IMU handles the heading for any.
Even when you're whacked around the
Yeah.
room?
Okay. And then, periodically, of course, when I'm looking for a can, right, the camera drives the robot. So it doesn't really matter what your position is,
Yeah.
right?
Yeah.
So you're just driving to this
Blob.
blob. And then once I pick up the blob, then I say, okay, where am I at? Because now I've got to go to a given location within the Cartesian coordinate, right? I'm going to a particular XY location. So
Let's
now
go.
I need to know, okay, I know where I need to go, so I need to find out where I'm at. And that's kind of the logic that I use, that,
But you're tracking the whole location the whole time, even when you're
Well,
scanning through, you're just not using it, right?
through odometry.
Yeah.
When I'm normally driving, I just use odometry. But in the can-to-can course, again, odometry is really only important when you're trying to drop a can off, right? Because it doesn't matter where you're at in the course, as long as you can find a can, that's where you need to go.
Oh, that's not exactly my question. Odometry is a method for recording where you are. It's not a method for navigating. So,
Right.
so you're running and collecting where you are the whole time you're searching for cans, even though you're not using it for navigating.
Right, I'm updating it
And
all the
therefore, it's
time.
current when you get a can and say, now I want to see how far off I got.
Right,
Okay.
Yeah, you said it's really not important until you get a can,
right.
but it really is important because you gotta track it all the time, because you can't just start.
Well, you know, it's like I was showing you where you're trying to qualify. In other words, you don't want to just update the position of your robot, you know, haphazardly, because then bad things can happen, right? So you want to have a fairly high level of confidence that when you change where, you know, the position that you think you're at to a new measured position, you want a high confidence that that new measured position is really where you're at, right? And that's what I try to do, like with the cosine angle and all that. So now I do know where I'm at. And like I said, the most useful part of it is the updating the X and Y nodes. How far am I from the center of the course? And then I can update my X value based on that position. Because I have high confidence that if I measure that I'm 2 inches to the right of where I think I am, I'm probably there, you know. So then you go ahead and you update that and say, okay, now I know from where I'm at, I can calculate the trajectory to get where I need to drop the can off at, right? Because the Y value there, as long as you make it through the goal, the Y value is not as critical, right? But you don't want to come running up to the gold and clip it on the side because your odometry's, you know, 4 or 5 inches off kilter, right? And when I was doing just straight up odometry with the heading and angles based on the odometry, I mean, things got south really fast, you know.
One wall hit.
Yeah, we've all seen that, you know. Okay, I got a can now, but I can't make it out of the course because I keep bumping into the corner. Because, you know, if your angle is just a little bit off,
Yeah.
and that's where that IMU really comes into play and really quite helpful.
One question, I understand how you found your width, but how did you find your location lengthwise since you got holes in the end?
When I passed through that hole, I looked for those edges. And because the only place on the course, well, I take that back, but I'm looking for that given that set width of the opening of the end of the course. And that's where I update my Y.
Because I understand it, you find the can,
Right.
then what you do is you measure to see where you are width-wise,
Just on the X plane, yes.
and then, but you depend on the fact that your lengthwise measurement depends on previous on your odometry.
Yes.
And then you update the odometry every time you go through the goal.
Right. I update the Y part of it, yeah. If I see that opening.
And you know, those are generally on the order. I can run my robot for about 3 or 4 minutes without it calibrated. Typically, those cans are 30 seconds apart, 45 seconds apart. You're going to maintain good odometry for those short runs.
Generally, yeah.
The reason I was grinning was because looking at those validity tests that you have to do, I picture in my own mind that those arise because you didn't see the thing line up and square itself off in a corner and say, okay, I'm square. And
Yeah.
no, you're not square.
Right.
I've seen that.
Yeah, you've experienced that, haven't you?
Yes, I have.
My tabletop robot uses 2 sensors lined up on the edges. And I've got the problem with corners,
Yeah.
but I can't put a center sensor because of the configuration. And
So you're trying to figure out how to qualify that alignment. I mean, it's the same, you know, that seems to be one of the bigger challenges in robotics is, you know, you can write algorithms like, well, let me just measure this and then boom, you know, we can make this assumption. But that's when you start making assumptions is, you know, when you make the ass out of you and me, right? That's how assumptions spell.
And mine works, if it runs along, and if one of the sensors runs off the edge, it rotates and squares itself up.
Right.
And my odometry is so good that I can run at least 2 or 3 feet before I lose it. So that's a real problem. My corner, I think the way I handle the corners is when I noticed how far I had to turn. And if I was going parallel to the edge, I had to rotate about 90 degrees. If I was running to the end of the table, I didn't have to rotate much. If I had to rotate something like 45 degrees, so that meant I picked up a corner.
Yeah.
That was my way of
So you're trying to qualify that alignment, right?
I just throw those away. I'm doing what Scott's doing. I come into the thing saying, okay, I believe this is 0. And if you're telling me I have to rotate more than 35 degrees either direction to line up, I'm done. I can't do it.
You could just switch to sumo, because then you don't have any corners on the round.
Yeah.
Yep.
Well, actually, I started, I don't know, I'd say started, but I was conceptually thinking about one of the tabletop contests and building a robot based on, you know, the mouse sensors. Because I had some old mouse, and it's actually an SPI interface. I was able to pull the data sheet up on the sensor. And I thought, you know, that would be a very accurate way to determine odometry. There'd be no slip or anything because you're basically, however those devices actually work, you know, they seem to work very
But
accurately.
you don't get rotation.
Well, but no, my plan was to have
Two of
two.
them. There you go.
And then you could,
Yeah.
you know, basically and use it just like a motor encoder as far as for the odometry, right? How many ticks do we have, and based on the difference in ticks, then that's our angle, right? I mean, conceptually I thought it would work, but you know, it was one of those ideas that never took off.
There's somebody posted the other day, there's some company that makes a device, I think they're for drones. It's basically that with a lens on the front of it, so you can get it away from the ground. And it's basically taking a high-res picture and doing tensor flow and giving you back a X and Y.
It's an optical flow.
Yeah.
I think that's what you search for, optical flow.
On your big parallel to the wall thing, I guess the other assumption you could, well, if you're in a corner, the center leg is going to be longer than the 2 side legs, or one of the side legs at least. So you know that doesn't occur in nature. Your center leg's never longer. So you would know right there that you're in a corner. So you know you could, right?
Well, it may not necessarily be a corner, it may be the wall of both, right? Because I think at some point, when do you reach the threshold that this is a sharp corner, right?
Yeah.
And when I was, talking about trying to write the algorithm this week, I kind of ran into that, because what I was going to do is I was going to triangulate on a corner.
Yeah.
But that says that you're perfectly 45 degrees from the corner, right? Which you can't really say.
But your center reading's going to be longer,
Look at
much
your
longer though.
differences, your
If you're trying to
numerical
find corners,
derivative.
you know, what you do is you take the derivative of the two readings, and what you'll get is you'll get a line that goes, there's a corner, there's a corner.
Well, that was kind of where I was going
But
with.
when you do that, you got to be towardish the middle, because as we said, if you look at those data sets that I told you about, if you're close to the corner, then the wall that you're up against is going to reach a point like with sonar, it's just not going to come back.
Yeah.
It's just going to go boing, boom.
So you have to have IR or
You have to be kind of, so the answer, if you really wanted to get your XY to the arena, you would move to the center and detect the 4 corners And
I think you can.
that's
do it-
really not hard to
You
do.
can do it with just one corner. You can square up in a corner.
Yeah, but I mean,
If
Based on
you
that,
know-
you're second to the course. And
you gotta remember, it's not probably square. I mean, we
Well,
tried,
But
but,
Scott and I both do the same thing, which is we go square the thing up before we do
Yeah,
our run.
and knock it around. Well, and actually, if you're gonna do that, it's much simpler to do the outside edges of the goals. And, you know, so if you're gonna triangulate and create odometry based on inside edges, the math would be exactly the same for using the edges of the goals, right? I mean, the angles would be a little bit different, but you could still orient yourself, and that's where I was trying to go with that, the edges thing. But one of the problems I ran into also was, as it was scanning through the goal, if there was something back there, you would see an edge in the middle of the goal, right? So I didn't just get 4 nice clean edges all the time. You know, there was garbage, you know, like as it was scanning through the goal. Or like you were saying, you know, in the can soccer, you know, if the other robot's tall enough, then that's gonna be an
You're
edge
gonna
too.
hit it, yeah.
So,
I don't
you know, there
if
were
this-
some other issues, so I didn't go that route.
I don't know if this would help Will, but since I'm also just using 2 sensors on a distance back, run the same problem. If you point it into your corner, you can get the same distance back. And you say, okay, well, this must be a level wall. So I actually have a 2-stage test. The first stage is to find 2 places where the 2 sonars are the same length. And the other one is to do this slight rotation. If it's a flat wall, then this one should get shorter and this one should get longer if I rotate it. And if I rotate this way, this one should get shorter and this one should get longer. And if they don't do that, it's not a flat wall, it's a corner or. a
Well,
wall
but,
surface.
but you could run into the same issue, you know, in a corner, right? Because if you're in a corner and you rotate, this one's gonna get shorter and this one's gonna get longer, depending on your orientation to the corner.
No,
Right?
Well,
If
actually,
you're-
the
if
way
you're-
I get out of that is because base algorithm, the one that's looking for the 2 things to be the same length, would at that point oscillate. It would fall into an oscillation. And I have a watchdog looking for the oscillation. So
Well,
you're right, that's.
You could do the same thing I do, line up to the wall, get the 2 readings equal, and then rotate a given amount, and then calculate the new distance.
That's
right?
basically what I'm doing. I use that to do 2 things, to tell me is
Yeah.
the wall really flat, and am I really normal to it?
Right.
And-
But see, with the extra data that I have, I can do that without
Yeah.
moving anymore.
So are you actually rotating until you're,
Yeah.
or do you just take a reading and correct yourself internally, say, oh, I'm not really 90, I'm actually 80?
No, I actually rotate, you know, I.
Correct yourself.
Yeah.
So this runs into a problem of how precisely can you control your robot? Because you're trying to, you know,
Yeah,
it's little
yeah.
tiny movements.
Well, if
Yeah.
you remember in that function, there was a limit to the amount of error that I was sending to the drive, right? So, and of course, that's all PID driven anyway, so, you know, but you're right, you have to have pretty precise control at those lower
Really
speeds.
slow.
And that's where, you know, the PWM and the motor control is really challenging, right? Because you have less encoder data to work with and, you know, and now you're trying to,
Slopping the gears.
yeah, slop in the
Yeah.
gears as well,
Or
so it's.
just nonlinearity, you know, at the low end of, you know, the motor's just, you know, barely able to move with, you know, a minimal amount of PWM or something. I
Or you
still-
overshoot too much because your eye is building up, and then you move too much.
Right.
Now you have to recover from it.
Yep.
Yeah.
At 30 degrees though, even if the wall's not perfectly straight, you're probably at 30 degrees on either side of, you know, a perpendicular.
Well, it's 15 degrees on either side, so it'd be 30 degrees total.
Oh, 30 total. But it would seem like even at 15, you should be able to sense, you know, if you're in the millimeter range, you know, those distances. So I don't know, to me, it seems like if you measure the center leg and it is longer than the 2 side legs, you know right away you're in a corner. So, but,
Yeah.
yeah.